let's talk about these two theorems. So remember, we already know two theorems. We know the intermediate value theorem. We have a continuous function on a closed interval. We have a point between f of a and f of b. I have to hit that point, that y value. And then the extreme value theorem is if I have a continuous function on a closed interval, I'm guaranteed to have an absolute max and an absolute value on that interval. So here's two more theorems. The first one is Rollens theorem. F of x is continuous on a closed interval a to b and differentiable on the open interval a to b. So we not only are continuous, but we just differentiable. If f of a equals f of b, then there is at least one point c in a to b such that f prime of c is 0. So let's draw that picture. So I have f of a and f of b. Those two values are equal, right? That's what it tells me. So I don't know where they are, but those two values are equal. If I have a continuous function that is also differentiable, how will I have to get from point A to point B? There are only two ways I can make that happen. Continuous differentiable. One, I could go straight there, horizontal line, right? The other way is I could curve up and back down. It does have to be a smooth curve, do you agree? Why does it have to be smooth? Why can't it be a sharp corner at the top? It's not differentiable. So we know it's a nice smooth curve. Would you agree that at some point on this interval, the first derivative is 0? Yes. If it's a horizontal line, it would be 0 everywhere. But at some point, the derivative is 0. That's what Rollens theorem says. We have a continuous function from a to b, differentiable on the open interval, and the reason they don't make it be differentiable on the closed interval is could the derivative be undefined at the points? And just still work out. If there's something weird like that, and still work it out. It could. So that's why they said it's only differentiable on the open interval. It doesn't have to be differentiable on the closed interval. So that's what Rollens theorem says. The mean value theorem is a more general case of what Rollens theorem says. Rollens theorem essentially says if the average rate of change between A and B is 0, then somewhere in between A and B, the instantaneous rate of change is 0. Right? That's what it says. Well, the mean value theorem is a more general case of that. We have a continuous function on a closed interval AB and differentiable on the open interval AB. But this time, they don't say that f of A and f of B are the same. So we have some point f of A and some point f of B. There's a lot of different ways that I could get from point A to point B. I could get there from a straight line, or I could get there with some sort of curve in between. The mean value theorem says that there is at least one point C in the interval AB such that the derivative equals f of B minus f of A over B minus A. What in the world is f of B minus f of A over B minus A? The slope of the secant line, right? Slope of the secant line from here to here, right? So there is some place on this curve where the slope of the, what's that prime? Slope of the tangent line is the same as the slope of the secant line. This time I have actually drawn it where there are two places like that. There may just be one, but there's at least one place between A and B where the slope of the secant line and the slope of the tangent line are the same. Any questions about that? Now let's put that into a real world context for a minute. This is the real world sound of the mean value theorem. The average rate of change on an interval is equal to the instantaneous rate of change at some point on an interval. If I'm driving from here to Fort Smith and I average 55 miles an hour at some some point did I go 55 miles an hour? That's what the mean value says. At some point on my trip, I had to go the average speed. So that makes perfect sense. It's almost as obvious as the intermediate value theorem, but still unnecessary. So that's what the mean value theorem says. Now, would that hold true if on my trip from here to Fort Smith, I averaged 55 miles an hour, but I stopped for 10 minutes at a gas station? Maybe I went 80 the whole time. I don't know, right? It wouldn't work if I make stops in between. So this only works if you're differentiable and continuous. So that's why those conditions hold. I guess I would have had to accelerate to 35, but pretend it's some other scenario where that would work. Okay, so determine whether Rollens theorem can be applied. If it can be applied, find a C that's guaranteed. Now, Rollens theorem does not tell you how to find C. We'll just have to figure that part out. But Rollens theorem guarantees a C somehow. So let's see if Rollens theorem applies and why or why not. What are my conditions for Rollens theorem to apply? I have to have a continuous function, and it has to be differentiable. Is a quadratic continuous and differentiable? Yes. So we're good there. What else has to happen? F of A has to equal F of B. Well, what is our A and B in this problem? 0 and 3. So what is F of 0? 0. And what is F of 3? 0. So, does Rollens theorem apply? Yes. I'm going to go ahead and write that down. F of x is continuous and differentiable. F of 0 equals 0 and F of 3 equals 0. Therefore, Rollens theorem applies. So that means there is a C between 0 and 3 where F prime equals 0. Everyone agree? Where F prime of C equals 0. So I'm going to find F prime of x. What is F prime of x? This is not Rollens theorem. This is just this problem. This problem tells me to find this. F prime of x is -2x. And I want to know when does that equal 0, right? At what C value does that equal 0? 3 over 2? C value is 3 over 2. Is that between 0 and 3? It is. It should be.
So can I write that F of C, but X is...
Yes, you could write it. C. Any questions about that? Okay, let's do the next one. Is G continuous? Wow. Yeah. Turned it. Yeah, it is. It's not taking long. Awesome. I turned it off, so hopefully that'll. Yeah, it's set on 72 and maybe you can hear it. Oh. It is turned off, so maybe it'll stay on. Okay, is x to the 2/3 minus 3 continuous? Well, it's a square function and a cube root. Are squares and cube roots okay? That's not okay. Where would we get issues? Maybe a square root. If the denominator was a 2, then we could have negatives or something like that. This one is continuous. Is it differentiable? I don't know. What do I probably need to do to find out if What did you say? Find the derivative. See if the derivative is defined. So what is G prime? Which is 2 over 3x to the 1/3 power. Is that defined everywhere? Where is it not defined? Is 0 between -8 and 8? Is that a problem for Rollens theorem?
Yes.
Now what if the interval was some other interval that didn't include 0? Would that be okay? It would. But we have a place between -8 and 8 where G prime of 0 does not exist. If you were to graph this graph, it has a sharp corner between -8 and 8. And the derivative between -8 and 8 is never 0 because of the sharp corner. So Rollens theorem does not apply to that. You probably don't even have to graph this one to know. Does not apply, why not? Sharp corner is the sharp corner between -1 and 1. It's at 0, isn't it? That's where it's an absolute value move down 1. So there's a sharp corner between -1 and 1. So Rollens theorem does not apply. Prime of 0 does not exist. Any questions?
You know that there's going to be a sharp corner, then you just automatically know that it's a sharp.
As long as that sharp corner is between the interval we're talking about.
Why in the first one did you plug in 0 and 3, and the next one you just went ahead and found the derivatives?
Well, remember on the first one I said, is this continuous and differentiable? And you said yes. And then I plugged them in. So I actually did that first. I asked, and we said, oh, the parabola is continuous everywhere, it's differentiable. For the others, I said, ooh, I don't know if that's differentiable or not. I found the derivative and looked to see if it was undefined.
So that's undefined.
It's undefined at 0. That makes sense. The other one, I didn't actually find the derivative, but I still thought of it. Kind of like the first one. Instead of actually finding the derivative, I just thought about it. So, okay, well, absolute values undefined at 0.
After I put a negative in the exponent, then it's going to be undefined.
Yeah, at 0. Now, again, if your interval doesn't include 0, then maybe that doesn't matter, but yes. Okay, so we're going to do the exact same thing with mean value. But if the mean value theorem can be applied to f on a closed interval AB, if it can be applied, find a c that's guaranteed in the mean value. So what's the first thing I have to ask myself? Rollens theorem or mean value theorem? Is the function continuous? Is the function differentiable? So is sine of x continuous? Is sine of x differentiable? The derivative's cosine, that's defined everywhere. Sine is defined everywhere. Looks good to me. So can the mean value theorem be applied? In fact, I don't even have to have f of a equals f of b anymore, do I? For mean value theorem. Only for Rollens theorem. So f of x is continuous and differentiable. So the mean value theorem, by the way, we're going to abbreviate MVT. So the mean value theorem applies. So the only two conditions I have to have for the mean value theorem to apply. Well, what does the mean value theorem say? That the average rate of change will equal the instantaneous rate of change, right? So the first thing I need to find is the average rate of change from 0 to pi, which would be sine of 0 is also 0. Could I have used Rollens theorem?
But just it equals something.
I could have used Rollens theorem, couldn't I? Because f of a equals f of b. Now, here's what you need to know. You could always skip Rollens theorem and use the mean value theorem. So you wouldn't have to memorize both. The Rollens theorem is just a little less work, isn't it? F of a equals f of b, and you would quit. So Rollens theorem is just a special case of the mean value theorem. So you would never have to know Rollens theorem. You could just skip straight to the mean value theorem. However, it's kind of nice because it's a little more efficient if f of a equals f of b. So that's 0. So what does that mean? So that's the average rate of change. It equals 0. So that means somewhere between 0 and pi, the instantaneous rate of change, which is what? F prime of x, we're going to write f prime of c, right? What is f prime? At some point, that must equal 0. That's what the mean value theorem says. At some point between 0 and pi, cosine has to also equal 0. What? That's it. When does cosine equal 0? Pi over 2. Now, cosine equals 0 at a lot of places. Why did you stop at just pi over 2?
Cosine 0 to pi.
Because it's in between 0 and pi. Perfect. There's guaranteed a c between 0 and pi, such that the average rate of change equals it. So let's look at the next one. What's the first thing I'm going to ask? Is it continuous? Is it? Where is it not continuous at? 1. Is that between -2 and 3? Done. It's not, mean value theorem does not apply because it's not continuous at 1. What would I get by plugging in? What would you get by plugging in?
That doesn't work.
It doesn't work. So you would ask yourself, is there anything that doesn't work? Is there anything that makes it not work?
If that was like x minus 2,
Then you'd say 2. If it was x minus 5, then I wouldn't care.
yeah.
Because it would be my interval.
Then what? Like, does it?
Then maybe the mean value theorem applies. We would need to go ahead and do the derivative, make sure the derivative exists. But the mean value theorem would apply. In fact, from -2 to 0, the mean value theorem here would apply. It's just when that discontinuity is on it. So, mean value theorem does not apply. G of x is not continuous at 1. The mean value theorem apply on the next one. What makes it easy to make that decision? There's no fractions. Polynomial. Polynomials are continuous and differentiable everywhere, aren't they? So polynomials are nice. Always continuous, always differentiable. So the mean value theorem applies. There will be a problem on your AP exam. I can almost guarantee. There will be a problem on your AP exam that will make you justify something using the mean value. You always have to make this statement. Before you use the mean value theorem, you have to say the function is continuous and differentiable. Therefore, by the mean value theorem, there's some C such that. So you will always have to make that statement that, hey, the mean value theorem applies. So, what do I do if the mean value theorem applies?
The average rate of change.
And I know that that equals, you wouldn't have to write that right here, but f prime of c at some point, right? So that's where I'm headed with this. F of 1 is 3. Is that right? F of negative 1 is negative 3. What is F prime?
Square.
If you don't, you could write X instead of C. No AP exam is going to count off because you called it X. Any questions so far?
Why did you just put the F prime C, right?
Why didn't you put a C after 2?
What's the derivative of 2?
Oh, we're taking derivative.
So I just took the derivative. You don't have to write it there. If you wanted to do like
That 3 is equal to that.
So this has to equal the derivative at some point. So this is just the derivative. You have to put the derivative over there. I did what I did up here. Just instead of doing a side note, I wrote it all in one place. 6 over 2 is 3. And can I solve that for C? Subtract 2 over. Divide by 3. Take the square root. What was my interval?
Negative 1 and 1.
Negative 1 to 1. They are both in between that interval. What if they weren't both in between that interval?
One was
Just 1.
You just pick the one that was, right? So pick whichever one is in the interval because you only want the value in the interval. Both of those happen to be in the interval, so pick those up. Just like up here, how we only picked 5 over 2 for that answer, you'll only pick the answer that applies. Okay, this is what the AP exam generally looks like with mean value theorem. Let's read this for a second. Oh, I passed it off. That packet is due Wednesday. No, I have it tomorrow.
What happened?
Try to have it done by tomorrow, but if we have a few questions tomorrow, we'll do a few questions. You don't come to the time for
If we go to like the arena and do like senior stuff, don't we?
your first class will probably be 5th.
So we can make it 4. 9:45. So we here till we don't come here till 9:45. And we do senior stuff.
Wait, we don't get to school. I bet football still have
Okay.
beer, so.
Alright, let's a test plane flies in straight line with positive velocity v of t in miles per minute at time t. V is a differentiable function of t. Selected values of v of t from 0 to 40 are shown in the table above. Based on the value of the table, what is the smallest number of instances at which the acceleration of the plane could equal 0 from 0 to 40? Now, I had one problem earlier in the year where I told you that acceleration was the derivative of velocity. You'll need to know that. So acceleration is the derivative of velocity. So it says, what is the smallest number of times when the acceleration of the plane could be 0? So when the derivative of the velocity could be 0. Well, that tells us that velocity is differentiable, which means it's continuous. Does everyone agree? So does the mean value theorem apply? Or Rollens theorem? In fact, I might want to use Rollens theorem on this one. I'm going to glance at the table. Here's what I'm going to glance at. Why would I glance at that? Between those 2 points, would you agree there has to be a place where the derivative of velocity is 0? By Rollens theorem. And what about from here to here? Everyone agree? So what is the smallest number of times that I could equal 0? I have to be 0 at least twice. And I have to be 0 between here and here. And I have to be 0 between here and here. Now maybe more. I don't know that. That's why it said what's the smallest number of times. So it does say just. Okay. So I'm going to do that. I prefer Rollens theorem on this justification. Why do I prefer Rollens theorem?
Good equation to plug in 2 points.
But I could do f of b minus f of a over b minus a. I could do slope. But wouldn't you agree I'd have to do that? I'd have to do 7 minus 7 over 15 minus 0. Wouldn't I have to show that for mean value? For Rollens theorem, I just have to say those are equal and those are equal. So it's a little faster for justification. Would mean value theorem work? It would work fine. It would just take a little longer. So what's my justification? So based on the values, what's the smallest number of times the acceleration of the plane could equal 0? 2. Why? Okay. B of 0 equals B of 15. Is that enough? What else do we need to say? Before that, what has to happen for Rollens theorem? Okay, is it? Yes. It says it, but I need to re-say it. B is differentiable. And therefore continuous. What do I mean and therefore continuous? If it's differentiable, it's continuous. So, by Rollens theorem, there are 2 places where f prime of c equals 0. And we'll do